Mic check, mic check. Sound check. Sound check. Alright, we are good and we are live. So, hello everyone. Today we're going to tackle another problem. So, it's another day in the series of Conquering Physics. And today's problem is we have a small puck of mass m is attached to a massless string that drops through a hole on a platform as shown in the diagram above. So I guess in order for y'all to see, I shall draw the diagram as best I can. So we have a platform here. We have a puck that is attached to the string, and the string falls basically down this platform. And let's see what else. The puck rotates at radius r when the tension of the string is T. So tension is T. This is the string is pulled downward until the radius of rotation R is less than little r is less than big R. So basically the thing's rotating around and we end up pulling it to little r. So little r is less than big R. And the question says, what is the change in energy of the puck when the radius is decreased? You may assume the puck is a point mass. Okay, and so here are a few different options we have. We have A, 1/2 TR. Remember, T is the initial tension, R is the initial radius, and it's big R over little r squared minus 1. B. So all these C, D, and E. E is 0. These all have 1/2. All these have T. This one's big R, little r, little r. And then the difference between here are just these flipped. Okay, and the reason why I'm writing them all out on this one is to give me time to think. Okay, and so again, with the basic principles we always mentioned, force body diagrams and energy. So in this case, I think we're mostly going to want to deal with energy. So there's an assumption that's had that they don't really say on here, that this puck is attached to a massless string. And then it says the puck rotates at a radius r, which implies that this puck is basically spinning here with a velocity v. And so when you have a tension on this string, that means you put a force inward. And so you basically have something that's rotating on a circle. And as we mentioned before, the acceleration is equal to v squared over r of this system. And so if you were to say the force, remember the force is equal to mass times acceleration. So this is basically just equal to mass times v squared over r. And so this is actually equal to the tension. Oh, and this puck has mass m, big M. And since all these responses don't really depend on m, then it's probably not going to matter as much as m. It's only going to depend on basically the radius that we have currently and then what we have after. And so what we notice is that in order for this puck to increase its velocity in this direction, the direction perpendicular to where the force is, you would need a force in this direction. right? And so because the only type of force you're applying when you pull on the string more is inward, then that's the only type of okay, so let's think about this real quick. So since the force is applied inward, the only difference in energy for this puck is that it's being pulled inward. So the velocity would actually remain the same for this puck. And so if we were to say Vi is equal to Vf, but as it gets pulled closer in, it's gonna want to fly out, and it's much harder to pull down. And so this is an interesting problem because if this is the case, the velocity is the same, and we're saying what's the energy of the puck. Well, the puck actually wouldn't increase in energy, so then our answer would actually be E. But let's try to still work out some more of this to make sure that we got everything in order. Because there is work being done as you pull this in. As there is a change, there is a force being applied on this and a distance because you're pulling this in. But I don't see the kinetic energy changing. Oh man, we might have gotten stumped. Okay, well, let's read the question. It says, "What's the change in energy of the puck?" And so the different types of energy forms in this is kinetic energy and potential energy. What can we really say there's a potential energy? Would this actually end up spinning faster? I know in terms of the angular frequency, it would. And so the work done on this would actually be the integral from r to little r, and then the force inward would be the tension, which would be a function of r. And the tension would be based on this if the velocity is the same. Which I believe it is. Times dr. And since the tension is technically negative if we consider the outward direction positive. So if we were to say this is our number line radius, we have r, little r. The tension is in the opposite direction. then this is going to be negative. And so if we were to integrate this, so this is the work done. This is basically the change in energy that we're calculating. And so this, and so just for reference, this is the change in energy that's being done by pulling this inward, but it's actually but I don't know if we could say that this is work being done on the puck, because I know when work when you apply when you apply a force perpendicular to the velocity of something traveling, all you do is change the direction. The velocity remains the same. And technically the only thing we would be, if we're pulling on this, is we're just changing the perpendicular direction of the trajectory. If we assume that we pull at a slow rate. And so this tension is equal to this. We'll say mv squared over r. So we'll call this r naught, or we could call this r prime to integrate appropriately. And so if we calculate this, the integral, is this correct? So does v depend on r? No. It's thing over 1 over r. The integral of 1 over r is actually the log r. And I'm not sure if this is correct. Yeah, this doesn't feel right. I made a really bad assumption on this. Does this make sense? So let's say if we were to make this close to 0, this whole thing would approach 0. Or this, no, this value in here would approach 0, which would mean this is like negative infinity, which means we had to put a lot of energy in the system, right? Because it's final minus initial. Okay, because this is close to 0, that could blow up to negative infinity. Negative infinity. And that kind of makes sense because you're trying to pull something that's maintaining a velocity v really, really, really close to the middle. So it'd get harder and harder to do that. I mean, if I was just to try to guess it, I would guess this. Because you can't do work on the puck to accelerate it or to move it forward in the direction of its path. Even if you pull it inward, it still has velocity v. And so the problem specifically says the change in energy of the puck. But for funsies, I'm just kind of calculating this to see what would be the change in energy overall in the sense of you pulling the puck. Because you constantly holding it, you are applying a force tension T here just to maintain it in the circle. The thing is, I'm still uncertain if this is correct. Well, you know what? That's why we have the Googles. Okay. Yep, if a particle experiences a constant perpendicular force, then its path is circular. Oh. Yeah, so it is a trick question. When a force component is perpendicular to the displacement of the object, such as when a body moves in a circular path under centripetal force, no work is done. Thus, no work can be performed by gravity on a planet with a circular orbit. This is ideal as orbitals are slightly elliptical. Yep. Okay, and I think this is why I like to do these, so that way we can get a more encompassing look of these things. Because the gravitational force is perpendicular to the motion. Why is there no work done if support force is perpendicular to the motion? Yeah, it says if you want to change the energy of an object, you need to do work on it. That's interesting because, I demonstrated a case that you are pulling on this string. You're technically doing work. I guess let us just type in the problem and see if we find something. I'm sure other people have worked this out, and I'm sure there's also a solutions to this. And you know what? There's no shame in looking it up, because that's how we learn. Hmm. Okay. Okay. Here's the problem. This one has numbers. A puck with mass 0.28 kilograms moves in a circle at the end of the string on frictional stable with this radius. The string goes to the hole and you hold it on the other end. The puck is rotating at an angular velocity of 18 rads per second. When you pull the string to reduce the radius, consider the puck. What is the new angular velocity of the puck? So this is interesting because this one poses it in terms of the angular velocity. And so the angular velocity will change because it's going to spin much faster. But the velocity is the same. I don't know if that makes sense. If you have a smaller trajectory to pass through, so if you have a circle like this compared to a circle like this, if you have the same velocity v on both of these, this one's going to spin much, much faster. So say the radius of this one is 3 times larger. This one will spin 3 times before this one finishes because the circumference of this is 2 pi r. And so if you plug in 1 here, that's 2 pi. If you plug in 3 here, that's 6 pi. So this one will spin 3 times before this one spins a full 1. Yeah, they did it in the sense of omega. Yeah, I think we'll just leave it at that. I don't know if there's much. I feel like there's more to say, but there really isn't much more. The answer is 0 because there's no work being done on the puck. It's just kind of it's a little bothersome that you technically can pull on this. So there's work being done somehow, right? Because there's a force being applied to a distance if you were to pull it in. That almost leads me to believe it wouldn't be 0. Because what if you did pull it in, right? I guess let's look at it from another point of view. Let's see how much energy technically you can extract from this. If supposedly you'd say you attach something really light here and you had this thing pick it up, such that um, the force is in the other direction, and this puck starts going further and further out. So let's say we started off initially at r and r naught went to infinity. Technically, if there is a constant velocity, this would go to infinity, and that means you could pick up something forever. And that really doesn't make sense. Yeah, because this r is 1 over r force, and you could basically just keep going forever, just letting something pull up. Yeah, that doesn't make sense. Oh man. Alright, we're actually gonna have to return to this problem some other day. Um, I don't think we were successful in this one, but we at least got stumped on something and have something to think about. Okay, this might be worth making a video on. Alright, yeah, but for now, I think we're gonna end the stream. Thanks for anyone who joined, and I hope you learned something. Y'all take care and have a good night.